Section 1-2 is on properties of real numbers. A real number is a value that can be represented on a number line. The set of real numbers contains many subsets. First of all real numbers are either rational or irrational, and the rational numbers can be written as a fraction. This includes terminating and repeating decimals. Here are some examples. So 2, -6, 3/4, 0.875, that's a terminating decimal, it ends and it can be written as a fraction, and 0.416 with the 6 repeating, that's a repeating decimal and that can also be written as a fraction. Irrational numbers cannot be written as fractions. This includes several special numbers such as pi and e, and all the square roots that cannot be simplified such as square root of 2 or square root of 3. These numbers are decimals that do not repeat and do not terminate. Within the set of rational numbers, there are natural numbers, whole numbers, and integers. The natural numbers are the counting numbers, so 1, 2, 3, 4, and so on. Whole numbers contain all of the natural numbers and 0, so starting at 0, 1, 2, 3, 4, and so on. Integers are all of the natural numbers, their opposites, which just means negatives, and 0. So from -1, -2, -3, and on down on the negative direction of the number line, and 0, 1, 2, 3, and on up in the positive direction. Here is a diagram from your textbook, which is actually a good visual representation of what's going on. So the whole big light green box is the set of real numbers. On this side, these are all the rational numbers, and this area over here are the irrational numbers. And then you can see that natural numbers is a subset within the whole numbers. Whole numbers are a subset within integers, and integers is a subset within rational numbers. Let's take a look at an example here. Bankers and investors use something called the rule of 72, which is modeled by the equation y equals 72 over x, where x is the percent interest rate and y is the years it takes an investment to double. Which set of numbers best describes y when x is a natural number? So if x is a natural number, so that's going to be something like 1, 2, 3, 4, and so on. Okay, so when we do 72 divided by one of those numbers, and actually all of those are evenly divisible, but let's say we chose something like 72 divided by 7, okay, 7 doesn't evenly go into 72, that's going to give me a rational number. Oops, sorry about that. So the set of numbers which best describes y when x is a natural number is the set of rational numbers. Here's another example. What is the graph of the numbers -5/3, -square root of 8, and -2.3 repeating? In order to graph these, and we're going to be graphing them on a number line, I need to turn each one into a decimal. So -5 over 3 is the same as -1.6 repeating, and I got that by just plugging it into my calculator. Square root of 8 is approximately equal to -2.8, and since that's irrational, it keeps going on forever. And here I have -2.3. So let's go ahead and draw a number line. And all of these are negative numbers, so I'm going to go ahead and put 0, -1, -2, and -3. -1.6 is going to be approximately right there, so I'll label that -5/3. -2.8 is going to be approximately right there, so I'll label that -square root of 8. And then -2.3 is going to be approximately right there, -2.3 repeating. And our next example says, how do the square root of 85 and 8.9 compare? So I'm going to grab my calculator and plug in the square root of 85, and that gives me approximately 9.2. And again, that's irrational and continues on. So 9.2 is greater than 8.9, so I can say, in comparison, the square root of 85 is greater than 8.9. The additive inverse of any number is its opposite. So for example, the additive inverse of 7 is -7. So that means that the sum of a number and its opposite is always 0. 0 is the additive identity. I can add 0 to anything and get the same thing back. The multiplicative inverse of any number is its reciprocal. So for example, the multiplicative inverse of 7 is 1/7. The product of any number and its inverse is 1, the multiplicative identity, which means I can multiply any number by 1 and the number remains the same. Here's a summary of some properties that you've probably seen in Algebra 1. So if A, B, and C are real numbers, then these are all of the properties for addition and multiplication. Probably haven't talked about closure before, but basically that says if you add two real numbers, you get a real number, and if you multiply two real numbers, you get a real number. The commutative property says that you can rearrange the order. The associative property says that you can put parentheses around different elements. You can associate them differently, and it remains the same. For identity, you can add 0 and the number remains identical. In multiplication, you can multiply by 1 and the number remains the same. And the inverse, for additive inverse, is going to be its opposite. The multiplicative inverse is going to be its reciprocal. And then kind of all by itself, actually using both addition and multiplication, here we have the distributive property. So here we have a couple examples, and it's asking what property is illustrated by each of the following equations. Number 1 is x times y times z equals x times z times y. So this is multiplication, and all we've done is rearrange a couple of the terms. So this is actually going to be the commutative property of multiplication, and you can feel free to go ahead and abbreviate like that. Number 2 says the quantity f times g times h is equal to f times the quantity g times h. Notice nothing moved around. We're using multiplication. I just used parentheses to associate terms differently. So this is going to be the associative property of multiplication. Number 3 here says the sum of P and Q times R is equal to the sum of Q and P times R. So this is a little confusing because I have both addition and multiplication going on here, but actually what's moving around, we have some movement around, but it's moving around with respect to addition. So this again is going to be the commutative property of addition. In number 4, we have the quantity 5 plus y times x is equal to x times the quantity 5 plus y. So what's moved around here is the stuff in the parentheses and the x. Notice they changed positions. The stuff inside the parentheses hasn't changed. So that's dealing with multiplication. So again, since they're moving around, it's the commutative property, and in this case, it's multiplication. Okay. Number 5, I have 8 plus 0 equals 0 plus 8. That, of course, is true. And what's happening is we're using addition and things are moving around. So that's the commutative property of addition. And our last example here has v plus 0 plus w equals v plus w. So all we did here on the one side of the equal sign is add a 0, which doesn't really change anything. It gives me the identical thing back. So this is the identity property of addition because I'm using addition. So in this section, we took a look at sets of real numbers and some of their properties and saw how to use them, how to identify them, and how to identify some of the properties.